All right. Thank you, Meghna, for the wonderful intro. Thank you, Scott, for the keynote. Really excited to be here today. My name is Eddie. I'm a product manager at SigOpt, now an Intel company for about the last year. Really excited to be joined by an expert set of panelists to discuss the topic of graph neural networks. So as Scott mentioned in the keynote today, the way SigOpt thinks about intelligent experimentation is through three main themes, being designing, exploring, and optimizing your models. So this panel in particular is going to focus on applying those three concepts, in particular optimization, to a very trendy new machine learning field called graph neural networks. So we've assembled, again, a set of experts from industry to discuss today, and I want to go ahead and start things off by giving everybody a moment to introduce themselves. So let's start off with Sasi from Intel. Sasi, could you say a few words about where you work, what your research interests are, and where you're joining us from today?
Sure. Thanks, Eddie. Hi, everyone. I'm Sasi Avancha. I work for Intel Labs. I've been at Intel for about 16 years now, and my primary focus is on high-performance computing and AI workloads, and primarily analyzing these workloads for Intel platforms and optimizing their performance for Intel platforms across the board, all kinds of hardware, including CPUs and our next-generation XPUs.
Awesome. Thanks. Da, could you go next?
Sure. Hello, everyone. This is Da. I'm a senior applied scientist in AWS AI. I have been working on, I was the initial, the DGL and a member of a DGL project. I've been working in the DGL project for over 3 years. And my interest is mainly on developing machine learning systems. And right now I'm working on large scale GNN training, graph neural network training.
Awesome. And Venkatesh? Oh, Venkatesh, I'm not getting your audio here. Still not hearing it. No. Yeah, do you want to try maybe plugging the headphones back in? I'm not getting it. Sasi, Da, you guys hearing him?
No, sorry, we still can't hear you,
Yeah.
Venkatesh.
Okay. Yeah, I'm not seeing it in the chat. Okay, well, I guess while we figure out Venkatesh's audio, Venkatesh, please let us know if you get it going. We can just start the conversation at Da. You mentioned DGL in your introduction. Could you just give us kind of the landscape of different frameworks that people are using in industry or training graph neural networks, scaling them up, and kind of give a little background around where DGL came from?
Sure. Nowadays, really a lot of people are working on develop systems to optimize for graph neural network training. A lot of work actually is from in the academia. Those work mainly is trying to explore what is the best way to optimize the graph neural network computation and how to scale it then into a large graph, right? And those work usually is not really try to deliver a platform for end user to use them. So in practice, when we talk about a user want to use a platform for graph neural network training, some of them, if you developing like very, very simple graph neural net models, then maybe we can just use like PyTorch, TensorFlow, and MaxNet, or any of those general deep learning frameworks. But if we really want to develop more advanced models, we have to rely on some, the more specialized platforms such as DGL, or the other one, the other very popular one is called PyTorch Geometric. And so some people, a lot of people actually are from academia. So the other group of people are from like industry, right? So for academia, the people will probably pick like a DGL or PyTorch Geometric. But in the real industry use, we want to scale a graph, the GNN training to a very, very large data set. Right? In that case, we have to use use many GPUs or many machines to train to really scale to a large data set. In that case, usually, the framework that provide this kind of capability are basically like DGL, and also some other framework from. I think there's quite a few graph neural network framework from Alibaba. This is a Chinese, a well-known Chinese company. I think this is the main thing. The platforms I have seen in the past, let's say 3 years.
Awesome, awesome. Thank you. Venkatesh, I saw you rejoin, and I see your picture now. Can you go ahead and do an audio test, see if we got you?
Yeah, sure. Can you hear me okay now?
Yeah, fantastic. Could we just rewind a little bit and give a brief intro again, where you work, what your research is up to, and where you're joining us from today?
Sure. My name is Venkatesh. Thank you, Eddie, for, I'm sorry about the audio troubles. No problem. I'm a director of data science, and I've been leading several large-scale applied AI research initiatives at PayPal. We are kind of practitioners, so we apply AI for a variety of applications, mainly around payment fraud, anti-money laundering, and credit and worthiness, and so on. So I've been in the industry for close to 25 years, and part of it in the engineering side of things, and mostly nowadays on the applied AI research side of things. So great to be here today.
Great. Glad to have you. So Dao was just giving us a little introduction on some frameworks, especially the kind of the comparison between PyTorch Geometric and DGL and academia versus industry. But if we could just even rewind before that, Venkatesh, since you're at the applied use case level, I'd love to hear you say a few words on kind of where the foundation of all machine learning is. What data models are we even applying these graph neural networks to? What use cases are these models relevant for?
Sure. Certainly, I think one of the fundamental difference before we dive into the graph neural network is how is it actually data represented? Right. So traditionally, all these e-commerce companies and most of the companies, you have data in some kind of tabular structure, a relational data store like Oracle or MySQL and so on. Right. But before you apply graph neural networks, the fundamental thing you need to think about is that you need to represent the data of graph structure in a graph form the first place. Right. So fundamental thing you need is some kind of foundational graph database. Right. So represent data of graph form in a graph database. Right. So once you have the data in that form, so several use cases which are actually, you have to see whether there are use cases are relevant to applying graph neural networks. So if you look at how the bad guys move money through the network, that's a typical graph problem, right? They move money from account to an account, and that's how do you track these anti-money laundering movements by representing graph and applying graph neural networks. That's one use case. And other big use cases are how are these accounts linked in some way, right? So you could have you could be logging in from IP address from Philippines, and I could be bad guy could be using a US IP address. Are these two accounts linked in some way? Unless until you represent the data as a graph and apply graph neural networks to figure out those associations, that's another use case where you can apply graph neural networks too.
Okay. Stassi, do you want to say a few words about working at kind of the systems level, thinking about how going from these data models that Venkatesh described, and we're talking about building kind of new neural network architectures, more complicated architectures. Can you just talk about a bit of the challenges at the systems level and thinking about how somebody who's maybe not just a pure data scientist who's trying to optimize models, but who's trying to design the overall system might think about different trade-offs with graph neural nets?
Sure, Eddie. I think what both Venkatesh and Das said perfectly dovetails into the system architecture challenges that we focus on within Intel, right? For example, and this is also part of what I was saying in my intro. Graph neural networks and the associated data sets are examples of these massive high performance computing kind of problems, right? And these workloads really stress the entire stack through and through from top to bottom, because you not only have to think of the end-to-end workflow, but you also have to think of each component within the workflow, and potentially where one of those components might become a bottleneck. And so just specifically in terms of graph neural networks, the way we think about the problem and sort of decomposing it is, first of all, what kind of models are you attempting to train? Is it driven by attempting to train the entire graph at once, so which we might call full graph training or full batch training? Or are you trying to do it using mini batches, which is the more traditional sort of neural network, in the vision space or the NLP space that you might use, where you use mini batches to train the graph neural network, right? So that is one sort of challenge that we have to address, and we have to ask ourselves for the given application. For example, what Venkatesh said, if you want to do this anti-money laundering kind of application, should you look at the entire graph as a complete entity, or do you do them as mini batches? So that's one problem to solve. Having done that, next you want to ask yourself from a system design perspective, how do you partition these graphs? So there are different ways of doing it. There are different algorithms. For example, there is the meta system, which will partition the graph along the edges. So there's edge cut, and so you now have graphs that are partitioned into, across different instances, CPU sockets or GPUs or whatever, and now you have to have interaction between those partitions. Another method is done by what is called this Libra library, which splits the graphs along the vertices. So you have vertex cut. And then there's another school of thought, which is, why even partition anything? Just partition the model. Forget about the graph. Just leave the graph as it is. So this is a set of systems, challenges that have to be solved. Third, once you look at these two aspects, once you've partitioned the graph, now if you want traditional graph neural network primitives, which primarily are aggregation of some sort, and update, right? So these are the two key things that you do. You gather features, feature vectors, you perform some sort of aggregation algorithm, and then you perform an update, and then you scatter back if required. So now, how do you do this when these graphs have been partitioned across remote systems? So now you have to have communications, and potentially you could have a situation where communication becomes bottleneck, and you don't want to have that happen. So now you design clever communication avoidance or communication reduction sort of algorithms to ensure that your communications don't become a bottleneck. And finally, last but not the least, once you've actually figured out all of these things, how do you actually get the compute to run efficiently on the underlying machine, whether it's a CPU socket or a GPU card or whatever it is? Again, to do both of these aggregation operations efficiently, as well as the update operations extremely efficiently. So these are the sort of high level systems challenges that we look at from a top to bottom perspective when we do these analysis and optimizations.
I want to pass the follow-on up to actually both Venkatesh and Da after this. But before that, Sasi, just to press into the first point you're making about kind of mini batch versus full batch sampling on graphs, could you maybe just say a few words about the distinction maybe for people who aren't familiar with graph neural nets but are used to kind of the mini batching process on ImageNet data sets or convolutional neural networks?
Sure. So when we talk about so full graph or full batch, as the name itself might suggest, involves no sampling of any sort. So assuming that you've decided you want to perform these graph neural network computations for, say, some number of hops, which basically translate into some number of layers, you simply take the entire graph, as it were, the entire data structure, apply your aggregation primitive on all of the nodes within that data structure, then apply your update algorithm on the entire graph. Again, it may be a simple matrix multiply followed by some linear layers some element-wise operator layers, things like that. And then you just repeat the same operation for the next set of filters, next hop, right? So you perform these multiple times. And that's on the entire graph. When you talk of mini batch sampling, what you would do is you would pick some set of nodes as seed nodes. And using those seed nodes, you actually create a sample that consists of a subset of the nodes. So in effect, you're extracting a subgraph from the entire graph, and you're extracting a set of such subgraphs. So your batch size, in effect, is the number of seed nodes, and those become the roots of your subtree, if you will, which forms subgraph. And then together, all of these seed nodes or these subgraphs, the seed nodes and the induced subgraphs, I should say, form the mini batch. And then you perform your training. You do exactly the same thing, except now you've actually extracted these subgraphs for as many hops as you've chosen initially at config time. So if you say I want a 3-hop network or a 3-layer graph neural network, in effect you've sampled graphs, sampled nodes such that you have a root, hop 1, hop 2, hop 3. So you have all of these, and that's the entire mini batch. And then you just train this, update the model, and then in the next iteration, you sample a new set of subgraphs and repeat until you've covered all your training data. And then at inference time, you simply pass the entire, inference, the test nodes, if you will, through the model. And that's how it works.
So it sounds like lots of kind of design decisions that might be a little novel to these sorts of models. That makes me think of kind of thinking back into the intelligent experimentation framework that Scott presented in the keynote of this conference. It makes me think of kind of the connection between those design choices and then what are the actual set of targets that you're trying to optimize for, constrain against, maybe track to make downstream decisions. So Venkatesh, for somebody who's at the applied use case level at PayPal, how do you guys think about what these design choices are actually, what you're trying to do when you tune these knobs, make choices about how many hops in the network? Should I do mini batch or full batch? What are the targets that you're actually trying to hit and constrain against?
Yeah, I think, Sasi, a lot of these choices available on the technology side of things. Before you apply one of these strategies, you have to have some kind of intuition about the problem you are solving. For example, in fraud is what we solve a lot, right? It's highly unbalanced. That means that there are a few bad guys in the graph network than the good guys, right? So less than 1% of the population are bad guys, right? But they account for like more than billions and billions of dollars in loss, right? So they account for a lot of the bad money movements, right? But their population is a lot less. So when you are doing these batches, you have to be making sure that the sample is also weighted towards the problem. Like, for example, you make sure that when you're sampling it, don't exclude all the bad guys in the population. You can't do a random sampling. So you need to have some kind of intelligent sampling before you figure out the batch, mini batch operation, right? In general, what we have found in practically applying is that if at all possible, try to fit the entire graph in a single machine with a large amount of memory and a lot of CPUs and horsepower in a single machine. And most of the, so that way that some of the problem which Sasi was saying about network communication, right, it's not becoming a bottleneck. And also, one of the fundamental problem is that when you're solving these problems is that analytical performance is extremely important, right? So one of the analytical performances, we want to make sure that we want to prevent a lot of bad dollar money movements activity. So the reduction of loss is extremely critical. In that case, you cannot partition the network, then you may not be able to optimize your analytical performance, which is going to be your dollar savings, right? Those kind of things. So these are some of the choices. Is you need to have your good optimization function, what you are trying to optimize. The problem you are trying to solve, make sure you have intuition around it, whether it's balanced or unbalanced problem. Accordingly, do the right type of sampling. And if at all possible, try to fit an entire graph in the memory if your hardware and infrastructure supports it.
So kind of some trade-offs maybe between the specific use case and kind of a more theoretical optimal performance across a bunch of different use cases there. I'm hearing, which I think actually segues nicely to asking Da kind of a similar question, but more at the DGL level, thinking about how you're designing a product that's more for a lot of different use cases of graph neural nets. How do you think about all the different sort of implementations that you might do to make distributed training available, or just in general scaling up available in DGL, and then hitting certain metrics in the platform? Like, what do you guys kind of optimize for when you're making these design implementations in DGL?
Sure. I mean, like from in the first, like from the user's perspective, right? So when we are dealing with a graph, a large scale, and people need to make a decision whether or not they want to use like a full graph training or mini batch training. And in the past, then because it is mini batch training or the how to sample mini batch for a graph for mini graph neural network is actually usually very difficult. So then a lot of as people initially people start with like a full graph training that works very well on a small data set. However, when we try to scale that kind of training method on a very large graph, like a graph with like hundreds of millions of nodes, and or even in Amazon scale, we are dealing with a graph with like billions of nodes, right? So we actually done that kind of experiment ourselves and see how well the full graph training works, and compare with mini batch training, where we can see like there's a significant performance. There's a significant the convergence speed difference. Like mini batch at full graph training can at that kind of scale can be like 1,000 times slower in terms of convergence, and also because for typical deep learning workloads, we have seen that it's very difficult to train a deep neural network with a very large batch size. And usually people will start to use a very special optimization algorithm or your method to when we're dealing with a very large batch size. Now we are talking about a batch size of like 100 million data points or even larger. That may even make it even more difficult. And we also observe that the model accuracy is lower when we do full graph training. After we wait for a couple of weeks. So that's why DGL, when we started, we actually at the beginning we choose mini batch training, and then of course, in terms of framework, we started with probably the most simple mini batch training, mini batch sampling method that is like developed by a model called the Graph Sage that is doing like node-wise neighbor sampling. So that each time we sample neighbors independently in each neighborhood, something like that. And then we construct multiple sample graph, and then we wrap all the sample graph into DGL graph structure, and then people can just run on this sample graph in the same way as people run like full graph training, very similar way. That is something we have discussed in this kind of APIs and try to spend a lot of time, trying to make the user experience the same as like full graph training. But of course, this is a very hot research area. A lot that each year we see different sampling methods and things like that. So when we design our API, we try to make it also very flexible so that people can use whatever sampling algorithm they want to implement. But this is still, because this is a research area, we try to, we expect that, eventually people will develop a much smarter sampling algorithm than what we have right now, and really speed up the training and speed up the convergence.
Sasi,
so I think Eddie also also just sort of take off from what Da said, and I think I'm going to sort of use this is still a research area. So I think one thing I don't know if Da is going to disagree with me, but I think it's still we do see even now papers. How do we do full batch training with better convergence and as much accuracy as what one might get with sampling and mini batch training, right? So I think that the area, and these things, I think for the moment are in a fairly bad state of flux, right? So what might be good for one kind of model where you sort of apply mini batch sampling, in another setting you might actually be better off doing a full graph sort of kind of thing, but where the sampling world and apply them to the full graph sort of training research. So, for example, can you make some of these things a little bit more approximate? Can you make them a little bit more noise into the training process, for example, and then therefore maybe you can get more optimal? Or conversely, can you take some of the advantages that full batch training has and apply it to the techniques that you would use in full batch training, and then apply, for example, historical embeddings, and then apply them to sampling, mini batch sampling kind of techniques, right? So these things are symbiotic with each other, should I say? And so sort of they play off of each other, right? So sometimes, and in fact, I should paraphrase what Professor Jurel Estovich, during one of our meetings, he said, "Look, full batch training and mini batch training have their own in this entire graph neural network training process." For example, if you were trying to analyze a social network with hundreds of nodes, for example, and his example was Lady Gaga's followers, you really don't want to do some analytics on Lady Gaga's followers, because there are hundreds of millions of such people, right? And it's impossible. What you really want is a very small sample out of that. And this is very similar to what Venkatesh said, that you only are looking for a very few bad guys in a large number of large who use their PayPal network. So for such kind of problems, mini batch sampling is probably more appropriate. But for some other settings, for example, if you were trying to do some plasma physics, you were trying to simulate plasma physics using graph neural networks, or use that simulated data to do graph neural network, you might be better off doing full batch or full graph sampling, full graph or full batch training, right? So each of these, I think, has their own importance, and so from our point of view, on the CPU, the most horizontal kind of platform, if you will, right? So it should be able to handle distributed full batch training, distributed mini batch training, all of this at scale, at extremely good efficiency, both and in terms of memory utilization. That's the other point that Venkatesh made.
Yeah, so to refer to a bit, a little more thing I want to mention is that when we discuss the full batch training and mini batch training, so I'm not saying that full batch training is bad or something. And what I'm trying to clarify is that, so I mean, there are different kind of data sets people care about, right? So like there is like chemical compound; those graphs are usually very, very small. So then we want to, in that case, we don't really need to sample subgraph from this small graphs, right, to generate a mini batch. In that case, usually we want to sample multiple small graphs, and then that construct the mini batch and construct mini batch. And then we, in each of the subgraph, so in each of the small graphs, we will perform the regular, graph neural network on that data set. But when we are dealing with like social network or any, a lot of other industry cases, Amazon graph or whatever, those graph, there's a single graph and many, many nodes. And I think in, PayPal probably the similar, that kind of graph, right? So in that case, usually people, if we run the full graph training, then we are dealing with, in a mini batch, we are going to deal with like billions of nodes. That makes training very, very difficult. So in different settings, different.
So, yeah, sorry to interrupt, but suppose you were to actually partition the graphs, right? So if you made each partition small enough to fit on some, any card or socket or machine, you'd basically scale it to thousands of such instances of cards or CPUs. Wouldn't that sort of then enable you to do either a full graph training, or then you could again make the choice whether you want to do full graph or mini batch, wouldn't you say?
Yes, I guess in the end, what we really care about is how much computation we perform and how much we can move the model to the optimal state, right? That is what we really care. So we should, in a lot of cases, people should try both cases, and also observe that sometimes full graph training actually generates a better model accuracy. And I saw that kind of result in a small data set. I haven't seen this kind of result on a large data set yet. So, but I mean, really this kind of data set, right? So, I guess people should try both and see whether or not that's some other issue.
Yeah, those are all great points, actually. The bottom line is that you need to make sure that you need to have an intuition. You want to make sure that what is the result you expect to see in your use case, right? That's why I think all these design choices, like infrastructure choices, help us, the practitioners, to decide, you know what, just because you're getting the result doesn't even make sense, right? You need to have this domain expertise to validate some of those results, right? So I think it's really important to have the DGL framework. We are heavy users of it, and the infrastructure about whether it's mini batch, for example, even partitioning, right? Because it's a long tail, right? A heavily skewed data set, you need to have much more intelligent partitioning. The Lady Gaga use cases, maybe you can't put every partition, look at that, because you have a huge long tail. How do you have much more intelligent partition around these long tail, right? That's also something need to consider. But the bottom line is that you need to have intuition on what, and the results the graph neural network or any algorithm giving you, does it make sense to you, right? So you need to have that eventually. I think automation is important, but eventually you still need a human to validate the results you are getting. It makes sense.
Right. Regarding to that, I can really send thanks to the Intel lab. Now DGL is going to support both distributed mini batch training and distributed full graph training. So then every users can have their own choice of whichever they want to use.
Exactly. Yeah. So another thing that I'm going to ask you is that, so I've recently started looking at this notion of meta paths, right? So people are saying, look, direct connectivity of nodes to nodes and just training using just the those direct hops, as it were, is no longer efficient. In many cases, it doesn't even work, and so we should now start looking at how do you represent a single sort of instance that you just it may in fact be a single node or a single edge or something like that, but then you still have to decompose that meta path into its compose the model update. So in DGL, are you guys have you started sort of thinking about it, and if so, how does that impact? And potentially I can think of ways that would impact how Venkatesh might think about his problem of this fraud detection. Actually, if you had meta paths of several edges that form one sort of entity, and then you could represent that, then you could actually try and do the model update based on that meta path, right? So do you have
sorry, the signal is pretty bad. I'm guessing you are asking whether or not DGL supports metapath based method.
Right, correct. Given that, given that this seems to be the next sort of frontier in terms of graph algorithmically, at least.
Yeah, I mean, like DGL, I mean, we actually, supports metapath based models. However, we never really try to optimize it for distributed training at this point.
I see.
So we are still trying to observe whether or not this metapath-based method actually has an advantage compared with other methods. Right. So when you are talking about a metapath, I guess you are we are dealing most of the time not most of the time. So when we talk about a metapath-based method, we are actually trying to talk about how to deal with heterogeneous graph, right? And for heterogeneous graph models, there are two types. One is like we do the message passing directly, and there are a bunch of models like that. And then there's the other category is using metapath-based method to sample neighbors that is multiple hops away, and then somehow convert a heterogeneous graph into homogeneous graph, and then do the regular homogeneous graph message passing. And we are trying to compare both. So far, our experiment result shows that the direct message passing actually works better. Mainly, I guess the main reason is that whatever we do with metapath is we are trying to forcing a rule that reconstruct the graph structure, which means that we may lose some information from the original graph, right? So,
I see.
If we use direct message passing, then we can, if the model can, really can learn from any, if we can train the model well, we potentially can learn everything from the data. So I guess that's the one of the reason that direct message passing in a heterogeneous graph actually works better. So and also make our model system design simpler and things like that. So that's why right now we are not really at the stage of trying to dealing with MetaPath based models.
I see. Okay.
One question I wanted to kind of bring up, and maybe Venkatesh, since we've talked about this a bit, you can start off here, is sort of the idea of picking a model for deploying and then maintaining that model. What kind of considerations come into play? Maybe you can just talk about PayPal's system in particular, or more broadly in the field of graph neural nets. What kind of extra considerations need to be taken into account for working with these models in a deployed system?
Yeah, certainly. Thank you, Eddie. So one of the key thing is traditionally, most of the industry are still doing these two parts approach. So you have a model trained in an offline world, and that model is used for online inferencing, right? So you have offline training and online inferencing. So what we are trying to do is we want to bridge this gap, because more and more things it's merging between online to offline, right? So when you do offline to online approach, there's a delay in taking care of, for example, the new fraud patterns, right? So it's constantly emerging and constantly evolving. How can we be ahead of some of these fraudsters by having more online learning, right? So some of this is where I think we have used SigOpt tools to a very full extent. So what happens is that what you want to do is that you want to make sure some of these parameter choices during the offline world, when you're training your model, you want to be intelligently chosen. You want to pick those parameters chosen in a way, in an automated fashion, rather than human having to fix these parameters, which will optimize analytical performance, in this case, fraud loss or whatever, right? So by picking these right choice of parameters and letting the tool to figure out the right choice of parameters, what we can do is we can update the frequency at which we are updating the model from offline to the online. It'd be a lot more frequent than, let's say, instead of every 1 month or every 3 months, we can have maybe model every day or model every few hours, right? So its key thing is you want to make sure optimize most of these processes in an offline training process by utilizing tools like SigOpt's hyperparameter optimization as a service, right? So that helps you to actually produce models more quickly. That means that you can also refresh your models using the new types of data much more quicker. So that's really important. And also the one of the key things which is different from online to offline is that in online cases, often cases you are given some kind of seed accounts. For example, can you tell me this account is linked to any other bad accounts we have in our system? So you are already given a seed accounts you are querying in the graph system for online inferencing. In the offline case, often cases is mostly open-ended, right? For example, okay, they have this huge graph. Can you find me all these nodes participating in anti-money laundering movements? Which means this is all versus you're not given a single seed account. So the computational challenges, the algorithmic challenges are very different in the offline use cases versus online use cases. So hope that helps to give you viewers to give some insight into those some of those things we are doing.
So Venkatesh, I just had one question from that offline perspective, right? So traditional graph analytics playing a role also in with graph neural networks. I've heard and I've read some papers where they say, look, maybe we can do some say triangle counting as a first initial step, as a very sort of pre-processing step, if you will, and then once you nodes are actually part of which triangles, then we apply graph neural networks for maybe for 1 or 2 hops or whatever, or for example between net centrality to identify the key nodes which are. So are you guys, do you see
absolutely.
that value in that?
Yeah, certainly. So triangle counting is actually very laboriously computationally extensive process, but we are using something similar on this. Like, for example, some of the things we are applying clustering algorithms upfront before you apply graph neural networks, right? But grouping
Right,
all these
right.
because combining clustering to graph neural networks, you can scale it to
Sure.
much bigger graph, because now you're looking with clusters which are actually much smaller in terms of the graph structure than the actual set of all the nodes in your so you have the
Sure.
representative samples using the clustering algorithm. Certainly, I think traditional algorithms still play a big role in scaling to a much bigger data set.
Correct. And therefore, I think that, Eddie, also going back to your initial question, that is a design problem that we guys have to worry about, because now if you're looking at traditional graph analytics kind of problems, trying to solve those, thing to do with your heavy duty systolic engine or one of these vector. This is just basic. I mean, to put it bluntly, it's pointer chasing, right? So you basically go from pointer to pointer. This guy is connected to this guy is connected to that guy, and only when you come to this compute sort of little bit heavier part, which is the graph neural network, will all these optimization engines or accelerator engines play a part. Otherwise, it's basically latency driven sort of. So that's all latency bound part, right? So you just have to chase pointers and figure out. That makes your systems challenge even more complex. If you have to do a combination, that's something that I think is very exciting in this field, right? So if you can actually get the goodness of both, then you're in a great space with respect to all of this and fashion. That'll actually get you both the accuracy and the performance.
So we have about 2.5 minutes left before we're all going to move over to the Q&A session. So before we do that, I just want to do a little round robin. Everybody take 30 seconds and give a quick comment about what you want to see people in the graph neural net research community or machine learning community more broadly focusing on in the next couple of years. So let's start with Sasi.
Yeah, I think I just maybe have used up my 30 seconds to just say this. And so this is exactly what I'd like to see. I'd like to see folks in the algorithmic of the page ranks and the between the centrality and the triangle counting and forget about it. Graph neural networks is the only thing to do, and we just apply those, because at some point the model is not going to scale anymore unless you start bringing in some of the intelligence, if you will, from the traditional aspects. And just as the traditional algorithm, people said, hey, to actually learn the structure of the graph, I need to sort of apply some neural net. So now I think we may have come a little bit of a full circle. We want to enhance the power of graph neural networks. We need to bring in some of the traditional analytics techniques and approaches, hybrid. That's something I'd like to see happen over the next couple of years.
Sure. So actually, what I really want to see is people can we can find many like killer applications for graph neural network, right? So we have seen like graph neural network perform very well in the case of fraud detection, and we want to see whether or not it performs so well in also can also outperform those baselines for like search or for recommendation or for all other important applications for drug discovery or on and so. Like we want to see, I really want to see graph neural network has like a significant breakthrough in our various applications. And of course, then afterwards, then we want to see observe how the model, the training method or model will evolve, to give good. So that will help to train to scale better or deliver better, model accuracy and so on.
And Venkatesh?
Scaling. So we are out of time. Scaling is the most important thing.
Awesome. Okay, love that. Concise to end it. We're going to head over to the Q&A session. So if you have any questions for Sasi Da, Venkatesh, or myself, feel free to pop over to that Zoom, and we'll be there to chat for the next 15 minutes.
Thank you.